All right, in this lecture we're going to discuss another classifier, one that's called a maximum margin classifier, or it's really a framework, a maximum margin framework, and the classifier we'll discuss in detail is called the support vector machine, or the SVM for short. And so what are we trying to achieve with the maximum margin idea? So remember, with the perceptron, that if we have two classes that are linearly separable, meaning that we can find a line or a hyperplane that perfectly separates the two classes so that all the data points in one class are on one side of the hyperplane and all the data from the other class are on the other side of the hyperplane. The perceptron will find that hyperplane, but running the algorithm, the perceptron algorithm, it will find the first hyperplane that it comes across and then terminate. So it just finds a hyperplane that separates the two classes, but it doesn't really give any sort of weight to one hyperplane over the other. Any separating hyperplane is equally good as far as the perceptron is concerned. So the idea of maximum margin is that not all hyperplanes are equally good. For example, if you look at this hyperplane, even though it separates the two classes, they're awfully close to the hyperplane. The closest points are very close to the hyperplane, and so we could imagine that if we sampled more data from the red class and from the blue class, we would start to have some misclassified data points given this hyperplane. So the maximum margin concept is that if we want to generalize well to new data, if we want to sample more points from the blue and the red class here and have it still be a good classifier, we should put the hyperplane, loosely speaking, right in the middle of the data. Mathematically, what that means is that we would want to maximize the margin to the hyperplane. What the margin is quite simply, it's the distance to the hyperplane of the closest point in the data set. So we take the distance from every point in the data set to the hyperplane, for example, this distance. We calculate it for each point, and then we pick the smallest distance. That's the margin. So we want to maximize the margin, meaning that we want to find the hyperplane that separates the two classes, but is as far away as possible from the closest data points in each of those classes. So when we say we want to minimize the generalization error, we are making some sort of an assumption on how the data is generated. For example, we just discussed with the perceptron that we don't expect this hyperplane to generalize well to new data because we expect to see some red class points down here and some blue points up here on the wrong side of the hyperplane if we sampled more data in the future. So with some approaches, like for example, if we assumed some distribution on the two classes, what I'm showing here is a Bayes classifier that uses a class-specific multivariate Gaussian with a class-specific mean and a class-specific covariance. So we've discussed this previously. We saw there that we would get a decision boundary that is curved like this. And this is due to the fact that the two classes in this case have different covariances. If we force the two classes to have the same covariance, we would get a line. With different covariances, we get a curve. And in that case, what the Bayes classifier is trying to do is find the decision boundary that cuts into the probabilities in such a way that the probability of making an error under this distribution assumption is minimized. So if we have distributions that we think are reasonable for the data, we can come up with these Bayes classifiers that will minimize the probability of an error. Max margin classifiers don't make any sort of distribution assumption on the data. So with a probabilistic assumption, we get these sorts of Bayes classifiers. If we don't want to make any sort of probability assumptions at all, so for example, we don't want to define distributions on the two classes, then the idea of max margin is that simply finding the hyperplane that maximizes the distance to the nearest points is the best that we can do. So that's the motivation of max margin classifiers. So in this lecture, I want to build up some of the intuitions and the mathematical ideas behind max margin classifiers. And the first thing to talk about is convex sets. So let's notice in the context of this data that we've been looking at on the previous two slides that when we want to find a separating hyperplane between these two classes, the placement of that hyperplane only depends on the outer points of the sets. What that means is that these points here that are inside the boundary of the data aren't in any way going to determine what the hyperplane should look like that maximizes the margin. Geometrically and mathematically, what that means is that we can represent each of the two classes by the convex hull. And what a convex hull is the smallest convex set that can be drawn around the data set. So in the next slide, I'll be more specific about what it means. Intuitively, you can kind of imagine that it's the smallest shrink-wrapped set around our data set such that the line of sight is maintained between any 2 points within the set. So if this is the convex hull of the red class, then any 2 points within this hull can see each other. There's a line that can be drawn between them, and it will still remain within the set. Mathematically, what it means is that the convex hull of a data set is all points that can be reached by taking weighted averages of the data. So let's let this data set in this red class be x1 to xn. These are n two-dimensional points. Then every point x naught in this shaded region, so every point, for example, this point, call that x naught. So it's within the convex hull. It can be reached by setting some probability distribution on the data. So let alpha 1 to alpha n be a probability vector. So all of the points are greater than or equal to 0 in this vector, and they sum to 1. Then x naught can be represented as a weighted combination of points in the data set. So every point that can be reached by taking a weighted combination of all of these data points form the convex hull, this shaded region. Any point outside of this convex hull cannot be reached by taking a weighted average of all of the points in the data set. So that's how we can define mathematically the convex hull of a data set. It's every single point that we can get by taking a weighted average of the data. All right, so let's define the margin. We've already said it. Let's define it one more time. The margin of a classifying hyperplane H, so that would be this hyperplane here, is simply the shortest distance between the hyperplane and any point in either data set, or equivalently, and this will be important when we analyze what the SVM is doing later, equivalently between the hyperplane and the convex hull of either of the two classes. So what we want to do with this hyperplane H is put it exactly in the middle of the two convex hulls. But of course, now the difficult part is how do we actually find this? It's easy to say that we want to do that, and it makes intuitive sense why we would want to do that. But now we need some sort of an algorithm that's going to actually find this hyperplane that cuts right in the middle between these two data sets.